The Michaelis-Menten equation is used to describe the relationship between the initial velocity of an enzyme-catalyzed reaction, V naught, as a function of maximum reaction velocity, Vmax, which is reached when all enzyme active sites are occupied, initial substrate concentration, and the Michaelis constant Km. Km is equal to the substrate concentration when the reaction rate is half of Vmax. Km is also directly related to an enzyme's affinity or attraction to its substrate. A low Km indicates a high affinity, therefore, the enzyme has a greater chance of binding to the substrate. We can use this equation to estimate enzyme kinetic parameters, for example, the maximum rate an enzyme can achieve when fully saturated with substrate. It provides insight into enzyme activity by observing how reaction rates change with varying substrate concentrations, and provides knowledge into how inhibitors affect Vmax and Km of a reaction. An example of this is when hexokinase binds to ATP during glycolysis to produce glucose 6-phosphate and ADP. This reaction occurs in the outer mitochondrial membrane of cells in our body. At first, there are many hexokinases ready to catalyze this reaction. So when ATP is present, the ATP can readily bind to the hexokinase to produce the desired glucose 6-phosphate and ADP. If the substrate concentration of ATP is increased, the reaction rate also increases. However, if the number of ATP in the cell is larger than the amount of enzyme active sites, the reaction cannot go any faster. This shows that Vmax has been approached. As seen in the graph, Vmax is never reached and only approached. Product is still produced when Vmax is approached, but at a constant maximal rate. Once Vmax is approached, increasing the substrate concentration no longer increases the reaction rate. Let's take a look at another example. Imagine it's Sunday morning and you're entering your favorite coffee shop. The baristas represent the enzymes. They have a maximum speed, Vmax, they can work at and a limited number of hands to produce the desired product, this being coffee. You and the other customers waiting in line represent the substrate who are giving orders to the barista. If you arrive at the coffee shop and only a couple other people are in front of you, the baristas are not working at their full capacity and can readily make your coffee. If another customer enters the coffee shop, the rate at which coffee is produced continues to increase linearly because there are still baristas that can take the order and make the coffee. However, if there is suddenly a morning rush and a long line of customers fills the shop, the baristas cannot handle it anymore. Even though all of the baristas are working as fast as they can, the customers still have to wait in the long line. At this point, the rate of coffee production has reached its maximum velocity. Similarly to the hexokinase example, if more customers enter the shop after the rush, the reaction rate will still continue at the constant maximal rate. In summary, the Michaelis-Menten equation is like the heartbeat of enzyme kinetics. It links the initial velocity of enzyme-catalyzed reactions with three key factors, these being maximum velocity, substrate concentration, and the Michaelis constant. This equation helps us understand how fast enzymes can work and what limits their speed. It's very similar to a busy cafe. Once the baristas receive enough orders, they can only make coffee so fast. So next time your morning coffee is taking a little bit longer than usual, remember that the baristas, just like our enzymes, are working at full speed and doing their very best.